I'm quiet. All right, maybe we don't start yet, Adi. How about now? Better? All right, now I can hear myself too, twice. All right, I think we are actually live on stream. So, hi everyone. My name is Sasha Zelenovic, and I work at Red Hat. I'm extremely happy that everybody's here. I've been organizing these meetups, obviously, with a larger team for the whole year. This is probably our 20th meetup this year, and it just makes me so happy when people actually show up. So thank you for being here. As I said, I work for Red Hat at Red Hat in the AI team there. And Red Hat loves vLLM. We're the leading commercial contributor to the project. About 25% of all the contributions to vLLM come from the team Red Hat. We also have about 10 core committers on staff, so we're all in on vLLM, and you're really in for a treat here. We're really excited about that. There's a few firsts here. First official European meetup, so really happy they happen here in Zurich, so thanks for that. This is also our first live stream outside of China. We've been live streaming meetups in China. 41,000 people showed up on the WeChat stream on last Saturday. So I don't think we'll break that number, but we'll be happy if there is 41, hopefully. We'll know soon. I'll let you guys know at the end how many people are tuning in. So it's great to see the vLLM community is strong here. All of the 20-ish meetups that we organized so far have been completely packed. There's been a wait list, and it's great to see that Zurich is exactly the same. We're happy we chose Zurich for our first one in Europe. So I just want to say a few thank yous. Obviously, you guys in the vLLM community. Thank you for Mistral for sponsoring this event. Thank you for IBM. I'm not going to name individual people because a lot of work went here that would just take forever. But thank you for everybody who was involved for putting this event together. So let me just show you the agenda quickly. So we have a packed agenda, and we really did go all out here. We have maintainers, project vLLM maintainers, vLLM contributors, committers, award-winning professors, right? So it's a really packed agenda. So we'll give you an intro to vLLM, and then for the power users of vLLM, we'll share a quick project update. We'll talk about quantization, which is a way to take these massive LLMs and make them more efficient, faster, using less GPUs while delivering, much better performance. We'll talk about the Mistral. Thanks, guys, for being here. The Mistral AI work with vLLM. We'll also talk about hybrid models, which are now first-class citizens in vLLM, and then go into distributed inference. Talk about llm-d, which is the orchestration layer above vLLM. So it's about to get technical, for sure. So I hope you enjoy today's meetup. Just one quick reminder is we'll have a survey at the end, 3-question survey, super quick. So if you can just keep that in mind. Any feedback that you can give us, we just obviously want to improve and make this better every time. So again, thank you so much for being here. I'm going to pass it over to Philip from IBM to say a few words, and then we'll go into our agenda.
Thank you, Sasha. So welcome from IBM. I'm Philip Speti. I'm the CTO for IBM Switzerland. So really happy and glad to host this first European vLLM here in Zurich at our IBM location. And as Sasha said, there are many people who helped, but just one person, Sarah, that in the back, she has a great applause. Because everything it's up and running is thanks to Sarah, who did a great job. Thank you. And therefore, thank you for being here. Without further ado, I'll hand over.
Yeah, thanks a lot. Hey, everyone. Glad to be here. My name is Michael Goen, and I'm a lead maintainer on the vLLM project. I'm on the Red Hat Inference engineering team. I'm a principal engineer there. We've been working on it since late 2023 on all sorts of things. So we'll be giving you a quick overview of vLLM, what's recent, what's important about it, and also giving a bit of a preamble to why we think this space is so interesting and important to work on. So first, at Red Hat, obviously, we're very much focused on open source software, and we think working on that with the community, with other companies, with other research organizations is the way to win. And we think that making AI inference software more accessible, more efficient, and cheaper for organizations to host their own models is the best way to democratize the use of AI and make it useful to everyone. And as you probably know, like the key turning point for our investment and your investment in this space was ChatGPT in 2022. But we and many others, made a bet that sort of, there's open source models then, they weren't really usable. ChatGPT was much more usable, but sort of believing in the spirit of open source, we keep seeing better and better and better open source models, and these getting closer and closer in quality to the leading closed source models where we are today. And we very much, just today we had Kimi K2 Thinking, which is a 1 trillion parameter open source model that is competitive with GPT-5 and Claude Sonnet 4.5 on humanity's last exam, and agentic coding tasks. So we're there. Open source won. And so, yeah, sort of the power of open, sort of the green dots over there versus the red dots, the closed source models have gotten closer and closer in terms of performance and, matching and commoditizing the intelligence that the closed source companies sort of pioneered with. Obviously, the advantages of open source models should be obvious to you. You can host them yourself. You can control who has access to them, what data goes in, what data goes out. You can fine tune them for your applications. You can control them. You can have all the security you need. And many people obviously find this compelling, and that's why the open source community has grown to be so large for AI and particularly open source models. And the reason why we're here today and why this is all centered around vLLM is vLLM is the key software abstraction layer and project that lives between, the hardware and the applications, here models. And that's why we sort of think of it in terms of open source software as the key Linux in this, AI race. So it is the important software abstraction layer for all the hardware and all the models, which we'll talk about why that's important and why vLLM turned out the way it has. So first, let's state what vLLM's original goal is, to be the fastest and easiest to use open source LLM inference and serving engine. Pretty straightforward. And the reason why vLLM has, or rather how vLLM has achieved that is by being really easy to install. It's just a pip install away or a Docker pull away. And it's going to run, on any, common GPU you want to run on. Like I mentioned already, it works on all the different model architectures, hundreds of them, and all the different major hardware accelerators. And it integrates with the open source community. Many open source projects, hundreds of them, if not thousands, build on top of vLLM as that LLM inference abstraction layer and build their special applications, whether it's reinforcement learning or agentic coding or document understanding and detection. All sorts of things build on top of, hey, how are we going to efficiently do inference with large language models? And so, we already mentioned vLLM is easy to install, but it's also very easy to use. We offer, it's a Python-based library with a very simple Python LLM class for easily getting started with, putting in whatever model you have on Hugging Face and immediately spinning up and compiling an LLM engine and offering generate interface, chat interface, also multimodal data, all sorts of ways that, like you would expect, to run inference on a model, but of course, under the hood, doing it very efficiently. Second, and maybe most important, offering a very easy to use inference server. So hosting a model as a server across whatever GPUs you're interested in. And importantly, once you have your server running on localhost 8000, you get a wide variety of endpoints like the chat completions API, completions, embeddings, responses, re-rank, all sorts of things, so that you can replace vLLM as, or use vLLM as your replacement for the OpenAI API you were using, or the Anthropic API you were using, whatever closed source model API you're building your applications on, not just the model you're using, but your application interface. vLLM can emulate that with any open source model that's capable enough to, be used in your applications. And now I want to talk about why vLLM has gotten so popular further. So a really key investment that vLLM made is relying very heavily on PyTorch. PyTorch, as you know, is the most common or most popular open source ML framework. And the reason why vLLM is able to have so much flexibility, both in model definitions and hardware support, is through its integration with PyTorch as an abstraction layer that the hardware ultimately implements its most basic operations through PyTorch, and the model definitions in open source are generally written in some form of PyTorch. And so through very close collaboration with PyTorch as a project, vLLM regularly uses the latest features and projects out of the PyTorch ecosystem, and is very much a power user of PyTorch and enhances PyTorch through this collaboration. And this is part of the reason why vLLM was a founding member of the PyTorch Foundation, joining DeepSpeed, and most recently Ray announced at PyTorch conference 2 weeks ago. Founding the PyTorch Foundation as a really important movement to grow and cultivate the peak of the PyTorch ecosystem, and hopefully the love keeps growing more and more. Even more examples of PyTorch and vLLM taking care of each other, finding issues and pull requests and fixes in each of the repositories through our very close collaboration. So we love the PyTorch team. Now on to vLLM adoption. So obviously, vLLM started in 2023 with the page attention paper and has quickly grown in terms of GitHub stars up to very steadily up to 60,000 GitHub stars most recently, with regular deployments of vLLM on GPUs reaching 500,000 concurrent GPUs that we know of. It's probably more, and over 9,000 members in our developer Slack working and asking questions about the project constantly. It's also turned into a very large-scale collaborative project as a result. It's not just popular, it's also well distributed, and many different contributors work on it. We're reaching pretty steadily over 800 PRs a month, which is a lot to deal with. And over 1,700 unique contributors have landed code in the project, and we're rapidly increasing that number these days. And as I already mentioned, we're spreading these contributions out across not only Red Hat, IBM, and Mistral, but tons of other organizations, either enterprise or research or community. And it's a really vibrant community as a result of that, and is able to serve a lot of different use cases. As I mentioned before, vLLM is able to offer the software layer that many of the different hardware platforms are wanting to implement in order to support all the different models they want to run. And so we have, these are all hardware accelerators that run with vLLM to some extent. We have various hardware inside directly in the vLLM repo, like AMD, Intel, NVIDIA, CPUs, Google TPUs, and many more increasingly that are working with vLLM as a hardware plugin through a common interface that we've defined that any hardware accelerator can essentially make a plugin, and they can load into vLLM as they need and continue their own development through the fixed software abstractions that we laid out. And many more hardware accelerators are on the way, hopefully, and it's great to see the excitement from the hardware community, and hopefully a lot more efficiency is gained for everyone that's interested in deploying efficiently. So next, there's obviously broad model support. It's not only about performance and flexibility, it's about supporting the models that people want to run, and we support easily 100 plus, maybe even 200 plus now different model architectures. Of course, all of the common state-of-the-art models, but also small ones that are forgotten along the way, and there's power users using those. And of course, we have day zero support for the key models on launch, often with the model definitions and features implemented and provided by the model vendors themselves, which is really great to see. And of course, we're not only supporting text-only models, we also have very good support for multimodal models. And so here we have the launches of Qwen 3 VL and DeepSeek OCR, which we were we're really proud to be launch partners for and offering day zero support for the leading, most cutting edge multimodal input models. And finally, we don't have to support the models directly in vLLM. Through very close integration with Hugging Face transformers, we were actually able to make the transformers model definitions general enough so that we can use them directly in vLLM, substituting in the key operations that vLLM needs to run efficiently, such as attention, fused MOE, linear layers. And we're increasingly expanding the flexibility of this, and we're already able to support text dense models, recently fused MOE models, encoder-only models. So many of the sentence transformers run in vLLM through this. Yeah, it's really cool to sort of try and reduce the amount of duplicate model definitions and possible sources of truth, especially as many people do training through Hugging Face transformers. And now with reinforcement learning, you want to make sure your training definition and your inference definition are lined up. Another key thing that vLLM focuses on is running these models efficiently across a variety, or rather a number of hardware accelerators. So we support many different types of parallelism in order to efficiently serve your model across all the GPUs within a node, such as 8 H100s, but also running a model across multiple nodes of GPUs, where you have non-uniform interconnects, where you have very fast memory or interconnects within a node. You have maybe less quick interconnects as you go across nodes. And we support tensor parallelism, pipeline parallelism, mixing those types of parallelisms together, expert parallelism and data parallelism, which is key for large mixture of expert models, which we covered a bit later, and disaggregating prefill and decode instances so you can start to more reliably serve your models with the latency SLOs you have, which will be covered, thankfully, later in this talk. Of course, a really important growing use case for vLLM is in reinforcement learning. As I mentioned, this style of training very, very heavily actually relies on inference as well in order to get rollouts and train the agentic models to be more agentic. And so we're happy vLLM is integrated and featured in all of these key reinforcement libraries and even more in the growing ecosystem there. Next, it's not only about training models, of course, it's also about using the models once they're trained. And vLLM is also trying to help out the community and try to define some sort of standard for what the right agentic interface for running these increasingly complex models are, where they want to intersperse thinking, not thinking, tool calling, and ultimately, working as agents for a long time before they come back to you and need more context. And so, with the GPT OSS launch, where we partnered with OpenAI, we support the responses API, so you can run the same applications that use the responses API on ChatGPT with vLLM with GPT OSS, and we've had several coding agent libraries build on top of that support offered in vLLM. Hopefully, this is some sort of standard, but we also support the messages API, which is what Anthropic uses and is used by Claude Code, for instance. And most recently, we landed support for this, and so you can run vLLM serve Qwen 3B with tool calling enabled and run it exactly inside of Claude Code and start hosting Claude Code and running it completely locally, which is really cool. And yeah, as more agentic coding interfaces are built on top and support the features we have in vLLM, and of course, the more capable models that are coming out, we're really interested to see how we can better optimize vLLM for the unique workload that agentic coding requires. Another key place where vLLM has to focus on is accuracy. vLLM is often treated as the reference implementation, and it needs to be correct, especially when models launch on day zero. First impressions make a strong impression. So we take accuracy very seriously and try to work with the model vendors directly to make sure that vLLM is both accurate on the simple evals and the tough evals. We do accurate tool calling, accurate long context, and try to force these things along. We also have recently devoted a lot of work to supporting batch invariance, a form of making the inference more deterministic, regardless of the load on the server. which is also really important for reinforcement learning, as we want to make sure that the inference code and training code matches up regardless of the load, so that the training happens on policy. Secondly, we really care about performance and reliability. We have a live vLLM benchmark dashboard on the PyTorch dashboard, and this runs on basically every commit of vLLM, so we can quickly get warned whenever key performance regressions happen on key models. This is really useful. Shout out to the PyTorch team for providing this. And yeah, we put our money where our mouth is, and most recently we spent over $100,000 a month on CI, so that developers working on vLLM, pushing their PRs and getting testing, can have very full testing happening for them, and they can focus on the important features that they want to see landed in the project. Now I'm going to cover some of the key focus areas we've had in vLLM over the past couple months. One really key one, obviously, is Torch Compile from the PyTorch side. Hopefully you are familiar with Torch Compile a bit. It obviously offers for vLLM what it says on the tin. It allows for automatic kernel generation and compilation of PyTorch primitives. And we do use this for automatic fusion with the various PyTorch operations we use directly in PyTorch in vLLM. However, one of the more interesting things that we like to use Torch Compile for, and we've improved with close code development with the Torch Compile team, is using Torch Compile to give us a graph representation of the model and start implementing custom graph level transformations, so that we can have custom operations that we author in CUDA or other languages for attention, for sequence parallelism, for all reduce, RMS norm, quant, very complicated sequences, and substitute these inside of the graph without needing to change or modify the model definition. We think it's really important to keep the model definitions as simple and pure as possible, hopefully written in just native PyTorch, and the optimizations that we work in vLLM and the fusions we work on can be applied regardless of the specific model definition, and just in terms of the operations of the model and what order they happen in. This takes the onus and the load off of the model vendors, who just get to upstream their hopefully simple model definitions. And as we generate more general fusions, we're able to see those speedups applied across dozens of models in parallel. Next, another really key thing, which the talk from Thomas Parnell is going to cover a bit. We've invested heavily in supporting natively hybrid attention models, which we increasingly see as the future of efficient LM inference. You see this recently with like Gemma, Llama 4, Qwen 3 Next, DeepSeek, a variety of different model architectures recently. And this just means we need to efficiently deal with each layer potentially having different styles of KV cache or state management. And we directly support this in vLLM through this hybrid KV cache coordinator, which does a lot of the work to coordinate these complex patterns in the leading models. Next, another abstraction we developed in vLLM is the KV connector interface. This is key for things like disaggregated prefill decode, which you'll hear about later, also for offloading KV cache and doing general operations on the KV cache in whatever way you want to define it. We use this in a very key way with Nixel and LM cache for disaggregated prefill decode. But this is ultimately an extensible interface where you can plug in custom KV connectors based on your research or business needs. Another really cool feature, which is actually a new type of parallelism, is decode context parallel, which was actually contributed by the Moonshot Kimi team. This is a key optimization needed for models that have a small amount of KV heads, such as MLA for DeepSeek, which only has one, because as you do tensor parallelism, you need to replicate the KV heads if you can't evenly divide into them, which means you have to replicate the KV cache, meaning you have duplicate KV cache across all 8 of your GPUs you're deploying DeepSeek on, which you can see here with the GPU KV cache size only being 600,000 tokens. But with decode context parallel, where we're able to interleave the KV cache between the GPU ranks, we're able to 8x the KV cache and thus get much higher throughput and support longer context workloads on the same number of GPUs just by not replicating the KV cache. Another really key place of development that we're really happy has landed soon. If you're familiar with vLLM v1 to the journey of vLLM v0 to v1, one of the key features or developments there we mentioned was important was piecewise CUDA graphs to allow for more flexibility in the model definitions and allowing for potentially complex operations like MOEs and attention operations. However, piecewise CUDA graphs still has a clear latency degradation. And so we wanted to expand this to now support a flexible form of CUDA graphs where we can have much more control over, are we able to do piecewise CUDA graphs or full CUDA graphs or no CUDA graphs, or do it for decode only batches or mixed batches. And we have this flexible CUDA graphs system, which are designed that we have a great docs page on. But the key thing here is now we have full and piecewise CUDA graphs on by default. So you have the best of both worlds. Flexibility when you need it, but low latency whenever you need it as well. Another key place we've been pushing recently and has actually been a great collaboration point with the community is something we call Model Bash, where this is an example of a layer of, or rather a transformer block of DeepSeek R1. And we open up and post an annotated profile to everyone of, hey, we're spending this much time in this matrix multiplication, this much time in this operation, and identify these places where, hey, it would be great if we had some custom kernels or opportunities for fusion. And of course, we've been working on squashing and improving the performance here ourselves. But we've opened it up to the community and we've seen a lot of people jump in and help out and become great new contributors as a result of joining in on the fun of performance optimization. So to recap, vLLM takes timely, accurate, optimized model support very seriously, and the community relies on us for this. We focus on having a wide hardware support ecosystem and defining the right interfaces for hardware vendors to define, just enough software that they can run, hopefully, a lot of models flexibly. We integrate and play very well with the open source community that builds on top of Inference as an abstraction. We work very closely with the PyTorch team and community and believe that's the future for ML frameworks. And we're the frontier and readily innovate with what is happening in inference systems research and what real users see and need in production. So hopefully, a bit more about some of those things and what we're up to, and are joining the community soon. So I will hand it over to Eldar.
So, hello everyone. My name is Eldar Kurtic. I'm principal research scientist at Red Hat, and the topic for today is going to be quantization in vLLM. So just so we are all on the same page, the quantization is a process in which we are compressing a model by reducing the number of bits that we use to represent either weights or activations or both. So if we imagine that we have a model whose weights are represented in FP32, and they have they're distributed across this Gaussian-like curve, we can see that they can take any possible value. So we have very high granularity here. Through the process of quantization, we are trying now to take all of these weights and we are trying to map them in a set of discrete buckets where each bucket corresponds to some specific value that we can represent in int4. And as you can see, we have much lower granularity in int4. And what's going to happen through this process is that for some of the weights which are close to each other in FP32, we will not be able to represent their difference in int4. So this means that we're going to have to put them in the same bucket. And during this process, we'll be introducing some error or like a quantization noise. And the entire game in quantization is how do we deal and how do we manage this noise such that we do not destroy the model, so that we get the model which is still usable but compressed in the end. The first kind of thing that we usually talk about when we talk about quantization is the main question whether there is such a thing as a lossless quantization, because it's a lossy compression, so we are like reducing precision of the model. And with the entire advent of LLMs, like community became very interested into any kind of techniques that would enable them to run models more efficiently on like a lower number of GPUs and slightly cheaper. One unfortunate thing that happened during this period is that a lot of quantized models started appearing in the wild without proper validations, without proper calibrated quantization processes, and so on. And then we ended up in a situation where there has been a lot of skepticism around quality of quantized models in general. And this prompted us kind of to, and this kind of brings us to the first like a takeaway message from quantization in general. And that's the fact that not all quantized models are created equal, meaning that during the quantization process, there is like a million different hyperparameters and knobs that we should be tuning in order to get the model in the end. And if we have like a quantized model which is not performing well, we should not blame the quantization as like the main root cause for this. We should like take a look at how the model has been produced and whether the proper like a calibration process has been done. And this prompted us, like in general, to write a paper titled "Give me a BF16 or give me a DEF," which is relatively easy to read and should serve as some kind of a data sheet where you can take a look at what are the accuracy performance trade-offs that you can expect from popular models for popular quantization schemes. So basically what we did, we took models from 8 billion in size up to 400 billion in size. We calibrated quantization process for 3 popular quantization schemes, which are supported in vLLM, FP8, Int8, and Int4. And then we ran a ton of evaluations. In total, we ran more than 1 million evaluations. Basically, we touched every single like open source eval that exists out there, starting from OpenLLM, Leaderboard V1, V2, reasoning evals, long context, arena, hard coding, multimodal, and so on and so forth. What we found during this investigation was that if quantization process is tuned properly for Int8 and FP8 model, we should always get like almost indistinguishable models from the unquantized baselines, meaning in a range of 98-99% recovery. Whereas for Int4, we do see slightly higher drops, but the models should never like completely destroy the accuracy of the model. So it should still be like a usable model in the end. One snippet of the results that we present there is like shown here in this graph, where we look at the reasoning performance, which represents basically an average pass-at-1 score across the popular like reasoning benchmarks, AIME, Math 500, and GPQA Diamond. And we look at like a DeepSeek R1 distill models from both Llama and Quant family, and then we look across all of the available sizes to see how quantization is going to behave at different scales. And then we, following the recipes from the Give Me BF16 paper, we quantize them to FP8, Int8, and Int4. Where for FP8 and Int8, we are doing weight and activation quantization. For Int4, we are doing weight-only quantization. Gray bar here represents the unquantized, like a BF16 baseline. And as you can see, the blue, which represents FP8, and green bar, which represents the Int8 model, we see that these bars are almost indistinguishable from the BF16, meaning that if quantization is calibrated properly, usually what you should expect to get is a model with 98-99% accuracy recovery relative to the unquantized baseline. The last model, like Int4, is a setup where we do see slightly higher drops, but the models. So we do see slightly higher drops, but the models are never destroyed, like in the sense that they are not usable. And usually what we have seen across all of the evals and all of the models is that if we calibrate Int4 properly, we should get accuracy recoveries in a range of 95% and above, which is still not terrible given that we are compressing like model weights by 4x. A standard setup in like academia and the research papers is take a baseline BF16 model, we quantize it down, and then we look how well we are recovering accuracy of the original unquantized checkpoint, which is a perfect and fair setup to compare different quantization algorithms, different hyperparameters, and so on. However, in the real world, there is usually a slightly different objective that we are faced with, and that's like more or less like a question of like what is the best accuracy that I can get by like following some constraints that I have inside my deployment. And that constraint is like very often just the amount of the GPU memory that we have at our disposal to deploy a model. And if there's no in the world without quantization, the best thing that we can do is we go to Hugging Face Hub, we see what's the largest model that we can fit inside our GPU, and then we take that model and whatever accuracy that model has, that's the best accuracy that we can get. Putting aside like additional fine-tuning, training, and so on. So just taking the models off the shelf. However, quantization offers this additional pathway that we can use like to fit inside the same like compute constraints, but get much higher accuracy in the end. And that's the process in which we can go to a larger model, which originally does not fit inside our GPU, and then we start quantizing down the model to a specific bit width that we can actually fit inside our GPU, and therefore leverage the accuracy of a higher model, even though if during this process, we could lose 1 to 5% of the accuracy, depending on the quantization scheme, we should still end up at a much better place than a smaller unquantized model. And like a perfect example here is like a Qwen 7B and Qwen 14B, where, for example, Qwen 7B in unquantized form, like a BF16, takes like 14 gigs of the GPU memory for the weights. If we go to Qwen 14B, it takes 28 gigabytes of the memory. So in order to bring it down like to the same like a GPU memory requirements as Qwen 7B, we can quantize it to FP8, Int8, or even lower like to Int4, and kind of benefit from this much higher baseline accuracy, and then like basically go from 65 to 74, 73, 72, whatever is the target scheme. So the second takeaway message is larger quantized is always better than smaller unquantized. And these first kind of two takeaway messages were mostly related to accuracy of the models, because that's the most obvious thing that everyone asks. Like when we quantize a model, it's a lossy process. We are like reducing the bit width. So it's like the most obvious question to ask first, like what happens with the accuracy. The second most important question is what happens with the inference speed up. So given that we have a compressed model, is there anything we can do to kind of accelerate the inference? So to improve either latency or throughput inside our deployment. So here we are looking at the graph of for a Llama 3.1 8B model deployed on a single A6000 GPU for some specific like a doc string generation use case. And we are looking how intertoken latency changes with respect to the number of queries per second that we are sending to our server. And we are looking at three different models. The first one is BF16, represented by the blue graph. So this is unquantized baseline model. Then we have Int8 weight and activation quantized model, represented by the yellow graph here, and Int4 weight only quantized model, represented by the green graph. And there are like three interesting regions to observe in this plot. The first one is when we have less than 4 queries per second coming to our server. So this is a setup in which we don't have large enough inputs to keep our GPUs doing matrix multiplications. So this is the setup in which the main cost for runtime that we are paying is basically moving the data around, because computation is for free. We don't have large enough inputs to keep our GPUs busy. And in order to accelerate the inference, we need to accelerate the data movement. In order to accelerate data movement, we're going to do the weight only quantization, because weights are that's the data that we need to move to tensor cores to do the computations there. And therefore, we quantize 16-bit weights down to 4 bits to accelerate the specific part of the pipeline. However, if we start like increasing the number of queries that are coming to the server, and we hit a point for this specific example of 4 queries per second and more, we are entering second regime, which is where we have large enough inputs to keep our GPUs busy doing matrix multiplications. So inputs are large enough to keep tensor cores like busy, and to make the time the time spent reading the weights completely negligible relative to the time that we spent during the matmals. So we are entering the second regime, which is called like a compute-bounded regime. And in this regime, the only kind of the best way to get the speedups is to use faster tensor cores. And to get the faster tensor cores, we need to have both operands of the matrix-matrix multiplication quantized either to int8 or FP8, because modern GPUs come with int8 and FP8 tensor cores. And then we get 2 times more flops just by quantizing both operands. And that's the second phase where now we are switching the regime where weight and activation quantization becomes a better choice for our deployment than int for weight only quantization. And then if we push even more, like we push even more queries per second, we get to the third regime where weight only quantization becomes a worse choice than just deploying unquantized model. This is because we are entering like a heavily compute-bounded regime, where the time spent like on loading the weights is negligible to the time spent during during matpulse, and the overheads which we had like to unpack the weights, which have been like compressed to int4, now start hurting us in this specific scenario. So the third takeaway message is that there are no golden bullets. You should understand your deployment by doing like a real-world benchmarking of the use cases that you think are representative for your deployment in order to figure out in which of these 3 regimes you are, and based on that, you can pick the proper quantization scheme. And yeah, at the end, all of the algorithms and all of the tricks that we have used to produce all these high-quality quantized models have been implemented in llm compressor. So you can just go there and like leverage predefined like quantization schemes, which have been tuned by our team. If you would like to run these performance benchmarks, like to see in which mode, which regime you are, memory bandwidth bounded or compute bounded, you can go to guide llm, which will be able to automatically enable you to automatically do some benchmarking and get graphs which are relatively similar to what I've shown here. And then you can see in which regime you are, and based on that, figure out which quantization scheme to use. If you don't want to do any of this, you just want to take like a high quality, already validated quantized models, you can go to Red Hat AI Hugging Face Hub. Basically, our team has already like released a couple hundred quantized models there, and we are actively releasing whenever there is a new model. In a matter of a few days, there will be FP8, int8, int4, FP4 checkpoints there, which have been already validated by our team to have at least 95% accuracy recovery and like a decent speedups in vLLM. One thing that kind of we became very proud of, because llm compressor is a relatively new project, is the fact that Llama 4 team from Meta also adopted it. If you recall from the Llama 3.1 series, they have released FP8 model, but they have used their own internal tools for this to quantize the model. For Llama 4, they switched over and decided to use llm compressor to do FP8 quantization. What next? The next steps? If quantization doesn't give you enough speedups for your specific use case, we have recently launched like a new project called Speculators, where we released a library for training of speculative decoding models. So you can train your own models, or you can just use Speculators to convert existing speculative decoding models to a format that vLLM understands. So you can just take Eagle Tree, Haas, or whatever is like state of the art right now, convert it, and then run it in vLLM. And we already have a couple of models which are open sourced inside Red Hat AI's Hugging Face Hub, and we'll be adding more. And now I'm going to hand it over to Dan to cover new FP4 formats for which is quantization for modern GPUs.
All right, so thanks a lot for this introduction. So today, so my name is Dan Alistar. I'm a professor at IST in Austria and also a researcher at Red Hat AI. And in some sense, my job is to really push the limits of what's possible to do accurately with respect to compressing these models. So today, I'm going to tell you a bit about our research. So in short, what Eldar described was essentially a picture in which we can do close to lossless quantization of in FP8 or sometimes even in int8 for weights and activations, and that's a great idea because it really, in some sense, it doubles your flops the way he expressed it. So, what we are really pushing now is whether we can actually go lower, and the next barrier we are seeing is essentially 4-bit precision. So I'm going to give you kind of a short overview of kind of what the state of the art is, because there has been work here already. So in some sense, what we the key barrier that we're hitting here is the fact that modern LLMs essentially have very large outlier values in their weights, but also more primarily in their activation. So to understand what an outlier is, you can essentially see the graph here on your left. So, or sorry, on your right. Essentially, these are extremely large values, like hundreds of times larger than the average value, and this essentially messes up things on quantization because they essentially will zero out everything that's kind of close to them, or will need to be clipped, in which case we induce very high error. So the basic idea to kind of understand how to get around this, or this is the idea that's been kind of floated in the literature in various guises, is essentially to replace this kind of linear layer, like WX transpose, where the weights are W and the activations are X, is basically going to be replaced by a variant where we pre-multiply each one of these operands, the W and X, with a matrix, and this matrix is invertible, so essentially we multiply with the matrix itself on one hand, this is the matrix R, and then with its inverse on the other hand, but then we apply quantization to these two kind of operands independently. Okay, so if we didn't have any quantization, R would just go away and we would have like a perfect recovery of the original output. So what we're doing here is essentially we're saying kind of quantization sort of commutes with the matrix we're applying, therefore we should be fine. And then the matrix R should have some kind of smoothing property that kind of just takes away some of these outliers, so it kind of makes things easier to quantize. And then once you have this image in your head, it's very easy to understand pretty much all of the methods that have been proposed for like weights and activation quantization, such as smooth quant and so on, because they're essentially just variants of, like they use sort of increasingly complex or fancy matrices to smoothen their input. So for instance, smooth quant just uses a diagonal matrix, for those of you who understand the method, and then Carrot, who's a lead author, I challenge you to find in the room after the talks, is essentially doing Hadamard matrices, and then there are people from Meta proposed essentially learning these matrices and so on. But the problem here is that if we try to go directly all the way down to 4-bit precision, unfortunately, existing techniques essentially break. I mean, they're okay for academic applications, but like what Eldar would say is that the model is destroyed. Essentially, we're dropping more than 5% accuracy, sometimes even so more than 10% relative accuracy. So the model is no longer kind of Pareto competitive. You're just better off taking a smaller model in terms of accuracy. Okay, so kind of the challenge we have been trying to solve is whether we can go further on this, and kind of NVIDIA, who also understands this challenge, they kind of try to address this by proposing a new set of formats, which are called microscaling FP4 formats. Okay, and interestingly, they proposed 2 formats. One of the formats is designed directly by NVIDIA. It's called NVFP4, and the other one is, in some sense, democratically designed by a consortium of hardware vendors, and you'll see how that ended up in a minute. So essentially, the basic idea here is the initial idea is very common, is essentially common between the 2 formats. We want to have a different grid. We define a different quantization grid, whereas int essentially has a uniform grid. FP4, these formats use an FP quantization grid, which is finer towards 0 and more relaxed towards the endpoints of the interval. Okay, so the grids are different. They're just truncations of a floating point. These are the same grids. Now, the second thing is that all of these values, we're essentially going to define a group size or a micro scaling size, which means that a set of kind of consecutive values, 16 for NVFP and 32 for MXFP, they're going to be quantized together. Okay, and so all of these values, they're going to share a single scale. Okay, so that allows us to, this finer grain quantization allows us to reduce the quantization error that we're going to have whenever we have to bucketize these values. Okay, and then the problem with this is that this leaves us with a lot of scales. Like, notice that if you have one scale, one value per 32 or 16 values, then this is actually already a lot of storage for a model that's like has billions of parameters. So what they do is that they quantize the scales themselves, and this leads us to the second key difference between these 2 formats, which is that like NVFP chose fairly reasonable FP8 quantization E4 M3 for the scales, whereas MXFP, this kind of openly designed format, chose a somewhat unusual scale to put it nicely, which is basically they are only quantize the scales to powers of 2. So we'll see what this leads to, but it's probably not a great idea. So okay, so we essentially have these microscaling formats which have some small differences between them. Now the reason why we're actually doing this is because we're able to get much faster computational support for Int4 and for FP4 operations in this context. So in particular, you're able to get 4x speed up on a B200 and 6x on a B300 GPU, and according to their sheets, and also this is something we verified in practice. So we have kernels, and you can you can validate these numbers. I mean, you essentially maximize throughput at larger matrix multiplication sizes, but you're able to reach these and sometimes even slightly exceed them in practice. Okay. So now the question is, do these formats, does the fact that we're quantizing weights and activations in smaller groups, does this actually solve everything? And we'll see that surprisingly, this is not quite the case. So this is just a snapshot of kind of results that we did, essentially rerunning a subset of the million experiments that he ran for the previous paper, and we are looking at these kind of numbers that are highlighted in red, which are the recovery model recoveries when we use a version of Int4 that's kind of microscaled to match MXFP4. This is what you have on the first 3 rows, and then we have NVFP4 quantization for weights and activations and MXFP4. And then what we noticed is a couple of kind of interesting things. But first, no format is truly lossless. This is not a silver bullet. Even with advanced techniques as a GPTQ or SpinQuant, we actually still drop about 4 to 5%, sometimes even more. So even with this kind of a pretty advanced format. Now, if we're to rank sort of formats by their best performance, we'll see that NVFP4 is the best. Int4 is second by a very small margin. It's very close to the experimental noise. And then MXFP4 is terrible. And it turns out this format is terrible because of the fact that it very aggressively quantizes the scales. So essentially, you get very high error on scale quantization. And then we noticed that this also methods that include rotations, this kind of adding this R matrix idea that I described before, do not help NVFP4, but they help Int4 and MXFP4 formats a lot. So they do improve accuracy as predicted by the original papers, but there's something odd happening with NVFP4 which cannot leverage this rotation idea. And then we noticed that some of the existing literature some of the methods in the literature do improve results a bit, but not very significantly. Okay, so this was the state of things that where we started at, and we were a bit puzzled because it's really not so clear why things are happening. So what we really tried to do better, and we ended up with a new method that really improves the state of the art and is specialized for these formats. It's called micro-rotated GPTQ, and you can find the paper on arXiv, and you can also find the code on GitHub. So essentially, the method combines 2 key ideas. The first is that instead of doing very large rotation matrices, which is what was kind of prescribed by previous work, we're doing micro rotations. Essentially, these are very small rotation matrices whose size matches the group size. So essentially, we're just mixing values within the same group. Okay, this is in some sense this comes because of essentially we did an error analysis, and we noticed that the original weight and activation distributions, they're fairly spiky. And then if you're doing very large rotations, they become normally distributed. But it so happens that these new formats like NVFP4 and MXFP4, they're actually not very good in terms of error recovery for normally distributed data. However, if you have essentially if you have a mix between normal and spiky distributions, turns out that you can actually, which is what you get if you do micro rotations, turns out that you actually can get good results by quantizing to this format. And the second idea is error correction. So essentially we have like not so great mean square error on the quantization for both weights and activations, but then we apply a new variant of the GPTQ algorithm, which is a sort of error correction weight quantization algorithm with some specific modifications to adapt to the FP format, which I'm not going to go into the talk, but I'm happy to talk about offline. Now, the key observation here, and this is why we really chose this route, is that we noticed that on modern GPUs, such as like the Blackwell line, even on the lower powered ones, such as the 5090, you can actually fuse these very small micro rotations into the quantization operation. Therefore, the sort of extra cost of the rotation is zero. So the method essentially has no overhead or negligible overhead over the original approach. So now let's get back to what we really care about, which is accuracy. And you essentially can see the accuracy of essentially our method and then various other variants. On your left-hand side, you have the NVFP4 format, where you can see that the MRGPTQ is really kind of outside of the margin of error for across all of these benchmarks. These experiments are done on the Platinum benchmark that was released by MIT earlier this year. So we see that we're able to get about 97% accuracy recovery. So we're really outside of this kind of 95% unfortunate sort of ceiling that previous methods had. And for some models, we're actually able to for larger models, we're able to get to 99% recovery. So we're within the range of FP8 at that point. And then we also noticed that essentially the GPT on the right-hand side for which presents the MXFP results, we're able to we're able to get around 95% recovery. So the format still makes things hard for us, but it's reasonable enough that it could be used, I believe. Okay, so those are our findings. So currently, we believe this to be the state-of-the-art method for both NVFP4 and MXFP4. Well, the same trends. I mean, you get much better results if you do weight-only quantization. This is supported in vLLM as well. Okay, so the key question now is, can we make this fast and can we integrate it with vLLM? And here, I really want to really highlight the work of my postdoc Roberto Castro, who is going to move to Red Hat AI next month. So essentially, he managed to implement all of these kernels, both for NVFP, MXFP, both for the forward pass and also for the backward pass, with support for the micro rotations in a new library called Qtless, which essentially is able to get to close to ideal performance in terms of speed up. So you can essentially follow the lines there, but we're essentially getting pretty much matching essentially the 4x speed ups that are predicted by the data sheets. And then we're able to get, for a larger batch size, we're able to get about 2x speed up in vLLM using these formats. So in terms of other, like, if in case you actually want to try this out, so this format is now supported in vLLM. So you can, if you have models that are packed to the correct format, you can run it. Currently, you would need to produce the models using my lab's sort of compression algorithm that's available together with Qtless. And then we're currently actively working on pushing all of this to LM compressors, so you can just use these much easier flows. Okay, and then I'll leave you with kind of one interesting finding, which is that it does one unexpected benefit, or perhaps expected benefit, of the MXFP format, because of this kind of simpler scale, like a simple scale structure. You actually get up to 20% faster matrix multiplication. So I think we're going to try to keep working on this. Maybe we can actually allow it to match the speed of NVFP and essentially get this extra 20% kind of for free. So I think that's the end of my section.
Hey everyone, so my name is Julian. I'm an open source engineer at Mistral, so occasional contributor to vLLM, and this is Patrick.
Sure. Hi, I'm Patrick. I work in the science team and also help on open source.
Okay, so we will introduce the training reasoning models using vLLM at Mistral. So we will introduce magistral mediums. So the paper is on archive. It was released in June, and kudos to all our science team to make magistral. So large reasoning models, it's essentially a model is, you can call it also policy for RL. And what you do is that you take prompts that you feed to the model that make completions, and you want the completions to be good. So you compute a reward, and you train the model based on the reward. So to dive in, so what kind of prompts you can have? Basically for reasoning, usually it's like math problems. So what is 2 + 2, or to sort, or also code problems, so to sort a list. So you sample these prompts, you give them to the model that will generate several answers based on this prompt. So sometimes it will be good, like it will say 2 + 2 is 4. Sometimes it would be bad, so it will say it's 5. And then you will therefore verify each of the answers to make sure that the model will be trained on the good signal. So to do that, you will compute a loss based on the rewards and the on the rewards and the logics computed by the model. We didn't give you the formula, which is a bit complicated, but you can find the formula of GRPO for magistral in the paper. And when you have the loss, for like for all deep learning models, you just apply gradient updates so that you can train your model. So to do that, we need several items in our infrastructure. So first we have trainers. So the trainer will be essentially the model, so where you will maintain the model weights and what will perform gradient updates. So usually it's implemented in PyTorch or JAX. And then you have a set of generators. So these are the ones that will compute the completions based on the prompts. So generators are using the latest policies, so the latest weights computed at that time to perform completions and output log probabilities for each of the prompts that you give. And these ones are implemented with vLLM. And then you have verifiers. So you have in for reinforcement learning, sorry, you have models for verifiers, but for magistral we didn't use them. We had several rewards computed, we could say like deterministically. So we wanted to enforce, for example, that the model was using the same language for the reasoning than the same language as the prompt. We also force that the answer was correct. We enforce that the length of the length of the reasoning was not too short and not too long. And this is implemented in various frameworks like SymPy, end-to-end model. So the vanilla approach for the infra is to load the trainer weights and load them inside, that the generator loads the trainer weights directly, and we send one batch of B prompts to the generator. So then we wait that the generator weights are loaded. We can then start to compute the M generations for the generator based on the batch. So you have M times B requests. And then you send the you compute the answers, and then you send the answers to the verifiers. And once the answers are received by the verifiers, you compute the M times B rewards that you send back to the trainer. And then the trainer will wait that all the prompts, rewards, and answers are received, compute the loss, and perform gradient updates. But this has several problems and is very slow, and I will leave it to Patrick to explain why.
Cool, thanks. Great. Okay. Yeah. So maybe we'll take another look at the vanilla approach, and I think it's quite obvious that people can already see that certain components are going to be idle when others are going to be run. So whenever you do a gradient update and you do a vanilla approach, the generator doesn't get fed anything. So the generator is idle. We don't generate anything. Similarly, when we generate, the trainer cannot train. So this is a big problem, right? Because you might train on thousands of GPUs, and you might need also tens or even hundreds of generators on GPUs. So we definitely don't want to have all these idle GPUs. Another big problem is that's the first point here is how do you actually transfer the weights from the trainer to the generator? When you think about models like I don't know, like DeepSeek, they have 500 billion parameters, so that's a terabyte in BF16 easy in terms of file storage, and you need to kind of dump that from the trainer and then load it into the generator. The reason why this is the first approach that everybody takes is because the topology that you use for training is very different than the topology that you use for generation. That's a big problem, right? This can take a lot of time in distributed file systems. Dumping that much data is quite slow. So problem here. Yeah, the problem of the different topologies also makes it even harder actually, because it means you somehow need to kind of consolidate the weights or remap the weights. Also, if we use vLLM for generation, vLLM doesn't necessarily have the same like weight mapping that we might use for training. So we might even have to change the values of the tensors, because vLLM, for example, merges QKV matrices. We might not do this in training. Also a problem. Next problem is that you usually want a deterministic number of requests in order to train. So when you say like, okay, let's say you want to have, I don't know, like 10 rollouts, and you want to have 16 prompts, right? So you want to have 160 requests, and you need 160 requests to do one gradient update. The problem is that if you start generating, it always happens that some requests are going to finish much earlier than others. So then that means that you spend a lot of time generating maybe just like one or two kind of strangler requests. Again, there's a lot of lost time. Then also very fun challenge in RL is that the length, the generation length changes during training. So in the beginning, you might only generate up to like 100 tokens. In the end, you can generate up to 10,000 tokens. So that also poses a big problem. And to make this slide even a bit more messier, now we have this is the last point I think I already touched upon, is the trainer's idle when we generate. Okay, so how do we solve that at Mistral for training? So the first obvious thing is you want to train and generate in parallel. You cannot train and generate in parallel when you want to be perfectly on policy. It's impossible. So what we do is like you're almost on policy. That means that you train and then only you update maybe the weights every 10 steps. That kind of means that, I guess, for 10 steps, your generators are going to be a bit of policy, but it's not a lot. It's 10 steps out of, I don't know, like 10,000. So you're not going to update after every, you're not going to update the weights after every gradient update. Next thing is, is the problem that, well, like some people also might intuitively just say like, look, we're going to use the same GPU allocation that we use for training, also for generation. But this also kind of means that then you have to stop training when you use the same GPUs for generation. So we want to use different allocations, and then we want to try to allocate as many GPUs for generation until the training becomes a bottleneck again. So if that's the case, if our generation we can generate as many tokens as we can consume during training, then we can have a balance. And then we shouldn't actually have any bottleneck if we can generate and train at the same time. Cool. And now I think the beauty of why this actually works so well for Magistral is that we kind of just updated the weights on the fly. So I talked earlier about how you would have to kind of dump 1 terabyte of data and then load it again. What we actually do is we don't dump it at all. So we know that our model topology sits on 1,000 GPUs that's allocated for training. They're connected with nickel to our generator GPUs. So we're just going to directly update the weights through nickel, essentially. We use NVIDIA's fast and NVLink for this. It still means we have to change the topology, and it also still means we need to potentially merge weights. So it is quite finicky, actually, to kind of have this FSTP state topology and then map it to whatever vLLM expects. So it's not just key renaming, it's a lot of kind of separating tensors and potentially merging them. And the fun part is that we don't even update the KV cache. So we just leave the KV cache as is, and we update the weights. And that's actually in the beginning when we tried this out and it worked, we were like, all right, that's cool. We didn't expect that. But surprisingly, the model generates pretty good answers with a kind of pretty outdated KV cache. Cool. And now also another beauty of vLLM that really helped us and they kind of solved this problem of increasing length in the training is that, I mean, thanks to page attention, you don't really think about length that much, right? You have a budget of kind of like paged pages, I mean, memory pages, and you can kind of just allocate them to whatever sequence you want. So whether you, I don't know, generate 4 sequences with 10,000 tokens, or you generate 256 sequences with, I don't know, like 128 tokens, doesn't really matter from the utilization point of view. So that's quite nice. In that sense, like it's not like we drop in utilization of the GPU just because our length gets longer, because vLLM will just use them up correctly. We still need more time though, if our length grows, because we're not going to get the same number of requests in the same time. But then you can just kind of spin up more generators automatically if you need during training. It's also fine. It's not. I mean, it's not great with Slurm, but it's fine. Okay, cool. And now to finish the talk, it's our beautiful slide that explains it a bit. And I think just what I want to show here a bit is these nice colors and how they go from yellow to red. They kind of shows our training steps. So you see maybe pi minus 2 and pi minus 1, pi I, and then pi plus 1. So these are graded update steps. And you can see that some requests, they might actually go through 3 gradient update steps where, and actually you can also imagine like if the model weights are updated every step there, but the KV cache just stays the same. And that works. So you might have certain sequences that are generated for like 3 kind of model updates, and it's still fine. So like weight updates, they have 10,000 tokens, and only the last generated tokens actually come from like a real kind of KV cache. The old KV cache that's still used is from old weights, but it works. Cool. I think that's it. Yeah, from our side. So if you have any questions also about this, just catch us later.
Hi everyone. So we are Mathis and Gael from Mistral. So we work in the inference team. So our job is to make our models run as fast as possible in production and make that reliable. I just want to have a quick forward. So we're both occasional contributors to vLLM as well. And I think like one great benefit of using vLLM is that we can have our science team tinkering with it, doing RL, doing training, well, EVAs and stuff like that. And we can use the same software in inference. And that helps us a lot, having a single source of truth, making sure our model runs as expected. So yeah, today we're going to cover disaggregated serving with prefilled decode. I'm going to cover the basics, and then Mathis will go into the nitty-gritty details of what we experienced in production. All right. Okay, so obviously, as Mistral, we are a LLM completion service provider. And when our users ask very important questions to our service, like what is France's top 5 best cheese, of course, what you see as a user is first the time it took, to get the actual first token. So we call that the time to first token. That's very important for users to feel some kind of responsiveness to your service. And then you have the latencies that you have in between each and every token. So the inter-token latency, we're going to talk a lot about these two during that talk. Of course, when you serve to many different users, you want to aggregate those metrics and monitor them. So looking at the median, for example, for the inter-token latency is not enough. We also want to track the P99, so the worst percentile of what user can get from using your service, and we don't want any degradation over the whole percentiles. So very simply, like how inference works. So very basic. You have a request incoming, and that will go through the prefill phase. That is compute intensive because you can process all the tokens in parallel. So you're actually able to leverage your whole tensor cores on your GPU. That's nice. And that way you populate your KV cache, and then you will go through the decode phase of that request. That is very memory bound. So for each and every token you're going to generate, you have to load all your model weights from your global memory to your tensor cores to the chip memory. To do that and to have a service that can accept multiple requests coming at different times, we do, vLLM do what's called in-flight batching or continuous batching that has like several different names. And the idea is quite simple, is that so you process one request at a time, but every time you have like new requests coming in, you can aggregate those requests. So you would have like here, the request A that's going through its generation phase, but also included with the context phase of request B and C. So that's nice because that way you're able to leverage your GPU resources a bit better because you can go through different prefill phase that really use all your GPU resources. Okay, so, but when you do this, there is something you don't want to have is high spikes of latency in the token latency, because every time you're doing some decode and another prefill request comes in, you're scheduled with that one at the same time, so that would take longer to process. And as a user, that's very bad because you will have your token streaming like suddenly staggering a little bit. And you will, that's worse in terms of responsiveness. And also, if we want to actually like make money generating tokens, we want to aggregate as many requests as possible to use our GPUs to their maximum performance. But if we do that, we're going to increase a lot those kind of latency. So it's difficult to apply in practice for like user-facing interaction like chat. So one of the solutions is to use prefill and decode disaggregation. So you would have the prefill phase and the decode phase on two distinct set of GPUs, so physically different. One, of course, set of GPUs will only do prefill, and another set will do generation. And that way, you never have prefill and decode schedule at the same time. So your inter-token latency is much more stable. Another side benefit that you have from doing disaggregated serving is you can actually optimize both deployments separately. You could, for example, having a different set of hardware doing prefill and generation. Since you know that for prefill, you only care about the number of flops you have. You might want some kind of GPU that have a huge amount of flops, but you care a little less about the memory bandwidth. Whereas on generation, you could optimize on having a hardware that has a better bandwidth. And also, like, talked a bit earlier about different quantization scheme. You could have, for example, having only weight quantization on the generation part to benefit from having the less memory bandwidth to load your weights, whereas your prefill would have a different quantization scheme. That also works with sharding your model. You could have like a different TP size or EP size for generation and prefill. So that has a lot of benefits. How that works in vLLM, so very high picture here. It's fairly simple. So there is a KV connector API that you can use for this. What you would do, for example, is send a request to a prefill instance and sort of like trick it into only doing prefill by only setting max tokens equals 1. So we'd only generate 1 token. And then when the request comes back to you, it would say, hey, my KV cache is here. You can contact like through Nixle, for example, to get it. And then you will send that to the decode instance that would fetch the KV cache and process with further generation. And our goal with this, so this is actual data that we measured on production. So what you see with the red line is the P99 of the inter-token latency. So as you can see, it's huge compared to the P50 that you can see like on the orange and yellow lines, for example. And what we want to achieve with disaggregated serving is going to that blue line that's a bit above the others, but completely manageable. So I will leave the floor to Mathis to explain that.
Thank you, Michael. So I will now cover the challenge of prefill and decode disaggregation. There is several of them. I guess the main one that you will encounter is usually the infrastructure. You have different way of doing prefill and decode disaggregation. One of them is through Ethernet, but if you do that, you will suffer high TTFT because basically the KV cache can be super large. For instance, on one of our older model, the KV cache can be up to 16 gigabytes, which is super high. And this is actually in int8, so you can imagine. And if you don't have InfiniBand, which is basically a way to communicate super fast between different nodes between GPUs, you will have high TTFT. Just for context, the greens that you are seeing over there, those are several hundred gigabyte per second. So to do so within vLLM, we are actually using Nixle, which is NVIDIA library that came out, I think, in March, and which use UCX as backend. They have several backends, but the one that we are using right now is UCX, and it's a way to leverage InfiniBand. InfiniBand is actually a challenge because you need to set it up on your infrastructure. And this is not easy. And obviously, you need to configure it and to have all the stack that is running. Then you will face another challenge, which is how do you correctly size your disaggregated instance? So usually when we talked about disaggregated, we talked about XPYD. X stands for the number of prefill and Y stands for the number of decode. So it's quite simple. You will have X number of prefill and Y number of decode. This sizing depends on several stuff. One is the model, obviously, and the hardware, because models won't behave the same way. But I think the most important part is it depends on your input-output sequence length distribution. The high-level overview of this is quite simple. If you have a super large, if you send a long context only to your model, you will be in prefill heavy. If you are generating only long stuff, so it's What happens when you are in reasoning, you will be in decode heavy. And there is some caveat with that. The first one is when you have a long tail distribution for the input sequence length, you, in traditional settings within vLLM, you will have high spikes on other requests. And the reason of that is because you need to enable partial prefill. It's something you can do with a long prefill token threshold, and you can increase maximum batch tokens on the prefill. It's something you can do because basically on the prefill pods, you are on prefill instances, sorry, you are only compute bound, so you can increase maximum batch tokens as you want. Another caveat is obviously you need to be sure that your model won't put too much pressure on your decode. So you much watch, look how your model will behave, especially in reasoning. And the last caveat is you need to be extra sure that you need disaggregated serving, because if you don't use your model much, so for instance for older models, or if you are on your local setup, in-flight batching is much more efficient resource-wise. Another thing that is quite important, it's also a challenge, is you need to be able to schedule your request. And the reason of that is because for a set of resources, so let's say you have 100 GPUs, 50% of them, let's say, will be used for prefill, and the other 50% will be used for decode. So half of them only will be able to handle the same workload. So the issue with that is that you can have load spikes, which is not great, and one side can have a float of work coming. So the way you can handle that is by scheduling, and this is something that you can do with llm-d, and we are working on this at the moment. And final but not least, you need to be aware of how your deployment is stable. So if your prefill crash because you are rolling an update, or because simply there is a vLLM bug or whatever, you need to be aware, and you need to be extra sure that your decode won't die as well. This stability has been greatly improved recently, and thank you, that's great. And yeah, the other issue you must be aware is when you want to upgrade your vLLM, they need to be compatible. It seems obvious, but when you are in production, it's actually quite challenging. And you need to keep the prefill and decode ratio. So for everything that I mentioned, there is a few metrics to look at. And you need to look at first at some metrics on the prefill, which is obviously the pending request in the queue, some metrics in the decode, which are also pending requests in the queues. And you also need to look at the total experience TTFT, which will correspond to the addition of the first TTFT and the second TTFT, because this will be the TTFT the user will see. And so if you are noticing some spikes, especially for P99 TTFT, that kind of stuff, you need to be aware that it is a scheduling issue, or you need to scale up some instances. Another optimization that you could do with Disag is you can trade a slight increase of the P99 inter-token latency to improve your median TTFT. And this is actually quite important because user needs to have a good TTFT, especially for small requests. And you do that by routing directly small requests to the decode. Why is that working? Well, the thing is you only increase little bits the P99 because you only route very small requests. But actually, most of the time, at least for us, our requests, like most of our requests are very small at the beginning. It's like, hi, that kind of stuff. And you want to offload that to on the pre-fill side. In general, total response time is expected to be better than in traditional deployments. So in conclusion, disaggregated serving improve the quality of service, but at the cost of increased complexity. That's kind of obvious, but like it needs to be said, because you need to set up InfiniBand, like I said, but it's actually very worth it for interactive application, high workload, and that kind of stuff. But you need to be aware that it's not always worth it. Correctly sizing XPYD is kind of hard. You need to look at the metrics I mentioned earlier. You need to be aware of your input-output distribution, and especially the long tail part. And you need to schedule the request properly, and the stabilities matters a lot. But at the end, I would say that disaggregated serving is quite nice. This is a snapshot I took a few days ago. You see some spikes over there. It's because we don't have on this setup at least scheduling yet. We do have today, but I did not update the slide. And the thing is, over there, you have a high P99 ITL, but it's way much better. And the reason is because on this setup, we actually routed a bit more, some more small requests. So if we want to reduce that, we need basically to have less small requests that comes to the decode directly. And yeah, I would like also to thank you as the vLLM team and the llm-d team for their collaboration and dedication on this subject and other stuff. And kudos to everyone that made this meetup happening. And I would like to make a special thanks to Robert Cho and Will Heaton for their significant contribution on this subject, and also because they helped me with a horrible bug. So yeah, and by the way, we are hiring. You can check our page.
Hello, everyone. Good evening. My name is Thomas Parnell, and I'm a principal research scientist at IBM Research and a committer on the vLLM project. And today I'm going to talk to you about the work that we've done to enable hybrid models as first-class citizens in vLLM, the kind of the journey from supporting these models as really a hack in v0 to like fully supported, well-integrated models in v1. Okay, so like before I get into what is a hybrid model, I want to motivate a bit why we need them. I think everyone in this room is probably familiar with attention, how successful it's been at language modeling. Like it's revolutionized the industry, right? And in vLLM, we have tons of super smart ways for implementing attention on modern GPUs. So this is including vLLM's dependencies like flash attention, flash infer, and so on. Techniques like page attention, flash attention, tile softmax, tensor cores, TMA quantization. Like there's so much amazing engineering that's gone into optimizing attention on modern GPUs. However, like despite all that, there are still some theoretical issues with attention which we can't avoid. In particular, when like sequences get very, very long, we have two main issues, right? One is that the state that we need to maintain between iterations increases linearly with the sequence length. So as we go to 1 million tokens, the KV cache becomes huge. And secondly, when we go to really long sequences, the time to do the prefill, which affects your TTFT, blows up quadratically. So these are like theoretical problems that no amount of engineering can really overcome. So like, why do we care? Like maybe like we don't care about long sequences. I just want to say why this is so important is that in the kind of applications and the way people use these models, we see increasingly longer and longer sequences. Just some examples here, like one is RAG, where maybe you look up a bunch of documents in some vector database and insert them into your prompt. Depending on how many documents there are, this can lead to really long prompts that you're sending to your inference server. Another example is agentic patterns, right, where you have a multi-turn interaction with the model. You ask the model to generate something, you do a tool call, you get the output from that tool, you pass it back to the model, and this process iterates, which can lead to really long sequences being handled on the inference server. And finally, we have like the kind of emergence of thinking and reasoning models, where we tell the model to think through step by step. We insert some thinking tokens. This again can lead to really long rollouts from the model that we need to be able to support. So like long sequences are important. We need to think about how we can support that in vLLM without ruining the performance. So I'm not going to give you like the whole history of state space models and linear attention. I'm just going to cover some developments over the last few years. I'm going to start from like 2021, which is this paper S4. So this is one of the first attempts to apply state space models, which have a long history, like control theory, connections to RNNs. This is not the first state space model, but this was one of the most successful approaches, attempts to apply SSMs to language modeling. So the equations I show on the top here are kind of the core idea. You have like a recursive mapping from an input sequence X to an output sequence Y. You have these matrices A, B, and C. A and B kind of take your inputs and map it to this latent state H. And then the C matrix maps H to the output. And what's really important to understand here is that this recursion, it's linear in the sequence length. So no matter how long your sequence gets, you're always going to do like T steps if your sequence length is T. Secondly, like the size, the dimensionality of this latent state H, it's constant. So unlike KV cache, which grows as your sequence length gets longer, the state H is constant in size. I'll come back to that more later. So like one downside of this approach S4 is that it was pretty good at language modeling, but certain things like selectively copying parts of the input and reasoning about things in context still were not very good. So that's where Mamba comes in, and my clicker is not working. Here we go. So Mamba kind of solved this problem with the selective copying and in-context reasoning by making these ABC matrices dependent on the time step. So they can vary at each iteration of that recursion. Unfortunately, like despite kind of being super good at these tasks, Mamba still was slower than attention on like moderate sequences, because the algorithm doesn't map nicely into matrix multiplications. So it can't use like the tensor cores, which are really like prevalent on modern GPUs like Hopper and Blackwell. So the Mamba 2 paper, which came like a year later, solved that problem. So they found a way of like introducing structure into this matrix A, which allows you to rewrite this whole algorithm as like a big matrix transformation from the input sequence to the output sequence. That allows you to use all of the tensor cores very efficiently. And what's super interesting in this paper too is they found a connection. They proved a connection between like this form of SSM to something called linear attention, which like brings in a whole other like subfield of models. This linear attention is described in this 2020 paper. The idea there is kind of different. They try to approximate the softmax in a way that lets you like fold it into the feature maps. So you kind of end up with a linear attention mechanism. This idea spawned like tons and tons of variants on that idea. I'm not going to list them all, but like one relatively recent one, which has been extremely impactful, is this gated delta nets. Here, again, it's like a linear attention variant, which they show can actually outperform Mamba 2 in terms of like quality on downstream tasks by better learning like associations between the key and value tensors. So like that's kind of the history. This is like an atlas of the hybrid models that we support in vLLM today. You see that there's quite a lot, and they're also like diverse, so they don't all do the same thing. I mean, one thing you will notice is that they do all use attention. So attention is still important. We don't see that going away right now. But in addition to attention, they all use like different Mamba or linear attention approaches. You see like a cluster including Granite 4 from IBM, as well as Nemo Nano from NVIDIA that use attention and Mamba 2 rather. So Mamba 2 is kind of super widely used. And then you see kind of towards the bottom models like Qwen 3 Next and Kimi Linear, which are relatively newer models that are using linear attention, like gated delta nets, or this Kimi delta attention, which is kind of a variation on the gated delta net. Finally, you'll see kind of a recent trend in these models is that they're combining this hybrid idea of mixing attention and Mamba with MOE. So these are kind of the three key components we see emerging in these hybrid models. Cool. So as I said, these models are diverse, so they don't all have the same architecture, but there are some commonalities between them, in particular in the way we need to be able to manage the state. So for attention models, vLLM manages the KV cache in blocks. So we say a block is like, a block is a contiguous region of GPU memory with enough space to store the KV cache for all layers of the model for like a small number of tokens, say 16. For like a representative example, a block corresponds to around 64 kilobytes in GPU memory. And as we know, as we like generate new tokens with an attention-based model, we have to concatenate to the KV cache. So as we generate more and more tokens, we're like appending blocks, we're creating more and more KV cache. Like Mamba or linear attention models, on the other hand, work differently. So the state is much bigger. So you have like a single, rather than like appending to the KV cache each time you generate a token, you have a single Mamba state which you update in place. And what's really important to know is like that state is huge compared to a KV cache. So like a block of KV cache is 64 kilobytes versus 2.57 megabytes for the Mamba state. So like for a single block, the KV cache is 40 times smaller. But when you go to long sequences like 128K, the KV cache becomes 200 times larger. So this is what why people are excited about these models and why they can deliver like massively higher throughput for like large batch sizes. So yeah, how did we like first support these models in vLLM? So we kind of hacked the support into v0 in the following way. So on the left-hand side, you see how vLLM manages the attention blocks. So we have one KV cache tensor for each layer, for each attention layer in the model. And then like interleaved across those tensors are the blocks, the attention blocks. The number of blocks, n, in this figure, is something that vLLM determines automatically. So when we start the inference server, vLLM sees, okay, I've loaded the model, I do some kind of forward passes, I see how much memory is left over, and I calculate how many blocks I can fit. This is like super nice feature of vLLM. Mamba state, on the other hand, in v0, you can see on the figure on the right, we just allocate like a Mamba state for the maximum batch size that we can support on the server. So what's the problem with that? The maximum batch size is something that the user chooses. And we had like a lot of problems where users were setting this wrong. If it's too high, you get like CUDA out of memory. If you set it too small, then like you're not fully utilizing the GPU. So this is like a bad user experience, right? We want to automate how to choose that. So the goal of this effort, right, was to unify how we manage KV cache with how we manage the Mamba state. Okay, this is like partly for elegance. We want to have like a nice clean way of doing it. But it also allows us to, integrate hybrid models properly with vLLM v1 and benefit from stuff like prefix caching, KV cache transfer, PD disaggregation that we just heard about, and like other cool stuff from vLLM v1, like the Torch compiler integration, better scheduling, and so on and so on. So like v1 is great. We want to support hybrid models. So before I tell you about how we unify the Mamba state with the KV cache, I need to explain like how vLLM supports a different kind of hybrid model. So hybrid models is a bit of an overloaded term. We can also use it to refer to models like GPT OSS, which mix attention with sliding window attention layers. So how we handle that in vLLM v1 is kind of shown in this figure. So I show this for an example, this Google Gemma 3.1b IT, which has 4 full attention layers and 22 sliding window attention layers. So what we do is we form what we call KV cache groups, where each KV cache group contains layers of the same type. So in this example, we have a group with 4 full attention layers, and every other group is like a sliding window attention group, and we do a bit of padding if necessary, because we want to ensure that all groups are the same size. And then how we store the state is shown on the right. So we have one KV cache tensor for each element in the group, so 4 in this example. And then the different KV cache groups actually share those tensors. So like we have attention blocks and sliding window attention blocks sharing the same data structure, which is really great. Like it allows us to do very simple memory management. We can mix attention blocks and sliding window attention blocks interchangeably, provided the page size, so like the size of the block in GPU memory, is the same for all of the KV cache groups. And maybe you already start to see the problem here for Mamba, is that the Mamba state is huge compared to the attention state, right? It's like 2.6 megabytes versus 64K. So how do we solve that? And this kind of may seem like black magic, but I'll walk you through. It's actually very simple how we solve this problem. Firstly, we relax the constraint that like the block size for attention and Mamba has to be the same. Secondly, we take the attention layers and we increase the block size hugely from 16 to like hundreds or thousands of tokens to ensure that the attention page size is at least like greater than the Mamba page size. And we can do a bit of padding on the Mamba, and I'll show you an example of this. Finally, and this is like super important, we have to ensure that the views into the KV cache tensor are compatible. And I'll show you an example of this shortly. Okay, so this shows you how we align the page. This is shown for like a real example of Nemotron Nano from NVIDIA. You see in the top, like the attention KV cache group, which has block size 16 and page size 64K. All the other groups are Mamba groups, and they have like a block size of around, the block size is set to the maximum model length. So in this case, 128K. But the page size is 2.6 megs. So this is the problem we have to solve. So firstly, we just select the block size for attention that's a multiple of 16, such that it's bigger than the page size of attention is bigger than Mamba. And then we do a bit of padding. So like, it sounds complicated, but it's really simple. You might already say block size 672. That sounds really weird. Like that's not going to perform well. I'll come back to that in a moment. Regarding how we handle the striding, this shows kind of how it worked in our first attempt, and this was horrible. It gave really bad bugs, and I spent a long time debugging this. The two like KV cache groups share the same view into a KV cache tensor. On the left, you see the way the flash in for attention backend like looks into that tensor. So you can see it has key 0, value 0, key 1, value 1. So it's laid out like block by block by block. The Mamba view, on the other hand, so Mamba has like 2 substates, the conv state and then the SSM state. And it's laid out in a different way. So we have all the conv states for all the blocks, followed by all the SSM states for all the blocks. And what happens here is like if you write to Mamba state 0, you kind of go and write data into that tensor in a way that doesn't align with what attention expects, and you lead to like completely corrupted data and really crazy eval results. So the simple solution to that is to change the striding, and we do like a lot of tricks like this to make all the different attention backends line up together. We have to change the strides to ensure that like the views are compatible, and writing to one block is the same thing across the different views. Cool. So like that's the main like points I wanted to make to give you an idea of how vLLM unifies the state management for hybrid models. But there was also a bunch of other work needed. So we had to do a lot of changes in the modeling code to support V0. And I think Michael mentioned in the beginning, CUDA graphs. These are super important for hybrid models because these like Mamba and linear attention mechanisms are implemented using tons of Triton kernels. And these kernels have like a high launch overhead. So you see like overheads on the CPU coming from launching lots of different kernels. And this is why piecewise CUDA graphs doesn't really give us enough performance, and we have to use full CUDA graphs. Yeah, finally, prefix caching is something we landed kind of recently. It's a bit experimental. Please try it and let us know if you have any problems. Finally, I mentioned the weird block size, right? So block size 672. Some attention backends like Flash Attention or Flash Infer support this really fine. Others, though, do not. Excuse me. So in particular, when you're running on Blackwell, we want to use the TRT LLM kernels to get the best performance out of the GPUs. And Blackwell, like those kernels only support block size 16, 32, and 64. So you can't just use some random value of like 718. So we've implemented something recently where we can decouple the kernel block size from the block size used by the KV cache manager. This is like super important if you want to use hybrid models on Blackwell. Okay, cool. So to kind of close, I want to show you some benchmark results. For this, we're going to use a Granite 4 model. So this is like a hybrid model that combines attention and Mamba 2 and MOE. It has 7 billion parameters, and 1 billion of those are active at like any given time. Then we use vLLM's like inbuilt benchmarking tool, vLLM bench serve. We use random data. So yeah, like prefix caching is not involved in this benchmark. We use quite long prompts, so like 32K in, 128 tokens out. And we sweep the concurrency from 1 to 4 up to 16. Yeah, like we used the last version of vLLM that supported both V0 and V1. V0 has now been stripped out, so you can't, with the latest vLLM, V1 is what you have to use. But as you'll see, it's great. So wait, how do I go back? Cool. So yeah, thanks to the Mistral guys for talking about what is TTFT, what is ITL. I'm going to use the same metrics here. So you see 3 panes. On the left-hand side, it is the concurrency against the TTFT. In the middle is the concurrency against the ITL. And on the right-hand side, the concurrency against the throughput on the y-axis. You see 3 different colors here, orange, green, and blue. Orange is V0, green is V1 with piecewise CUDA graphs, and blue is V1 with full and piecewise, which means we use piecewise for like batches that include prefill and decode requests, and full CUDA graphs, so decode only batches. And what you see here is like for the TTFT, V1 is consistently better. This is coming from like the Torch compile integration. For the ITL, like if we only use piecewise, V1 is actually worse for low concurrency. This is coming from what I said about the overhead of launching Triton kernels. It's super important, especially when you're using like MOE and the latency is very low. But we see when we use full and piecewise, we recover that gap, and the ITL is like consistently better between V1 and V0. Similarly for throughput, we see like 31 to 91% higher throughput when using full and piecewise CUDA graphs in V1 compared to V0. Yeah, finally, I just want to say it's so great to see so many like local fans of vLLM and people interested in this work. I'm based locally here in our research lab in Rüschlikon, just down by the lake. We work tons on LLM inference, also on other topics like model architectures. We're working on supporting IBM's own accelerator Spire in vLLM. If you're interested in this stuff, please come and find me after the talk, and yeah, happy to talk. Thanks.
All right, I'm Tyler Michael Smith. This is the last talk, which will be hopefully pleasant news. If you, like me, you are very hungry right now. So I'm going to be talking about llm-d. So this is a distributed inference framework that we have built around vLLM. Right, so the way we kind of think about the inference stack is, vLLM is the inference server that really connects the models here at the top to the accelerators down at the bottom. And then we've got llm-d, which is the Kubernetes-based distributed inference framework that we use to orchestrate and put in like a lot of distributed optimizations. And it's really about optimizing inference performance, and it's about improving SLO targets. And so, okay, question is, okay, why llm-d? What do we have to do special? Why can't we just use Kubernetes as is, inference gateways? So, the big difference is, between LLM requests and modern HTTP requests are, HTTP requests are cheap, they're uniform, they're fast, they're stateless a lot of times. But LLM requests are slow. You can't predict how long they're going to take beforehand. They're non-uniform, very expensive, and they're stateful. We have to manage the KV caches. And they're orders of magnitude more expensive per request. Okay, so yeah, like I said, llm-d is really about bringing together vLLM and the Kubernetes community. And this is an architecture diagram. So just to kind of trace a request. So a request comes in, hits the inference gateway. It does a gRPC call to this inference scheduler. So this is the endpoint picker that decides what vLLM pods a request should be routed to. That then comes back to the inference gateway, which then sends requests to the vLLM pods. And there may be pre-filled decode disaggregation involved here, like you heard during one of the Mistral talks. And so we kind of have, in the llm-d community, we have these 4 well-lit paths. These aren't like productized solutions. These are really ways of showing people, companies, users a way to kind of walk the path to get to a really good deployment, a good opinionated deployment in a specific case. For llm-d, basically to highlight the features that we have in the project. So the first is intelligent inference scheduling. And then I'll walk through all of these. So intelligent inference scheduling, like I said, we have this endpoint picker that decides which instances of vLLM a request should get routed to. And we have a couple of different routing algorithms in there. So one is load-aware routing. So every 200 milliseconds, the endpoint picker will scrape the metrics of all of the vLLM pods. So it knows exactly, how many requests are in flight for instance, and can use that to route to specific, pick the pods that have the least load, essentially. And that's kind of good in all cases. And we also have something called prefix-aware routing, where there's a couple of different flavors of this. So one, the endpoint picker can keep track of where it's routed requests in the past. And we're taking advantage of a feature in vLLM called automatic prefix caching, where if you're processing the same prompt multiple times, since the KV cache has already been processed, on subsequent requests, it doesn't have to be processed again. So the endpoint picker can take advantage of this and route to the same pods that it thinks has those prompt prefixes already processed. We also have something called precise KV scheduling, which we have something called a KV events API, where the vLLM pods will report back to the endpoint picker when they add or evict blocks from their KV caches. So in that case, the endpoint picker can know really precisely what's in cache. And this is really good for multi-turn conversations, like you talking to a Slack a chatbot, or it can be really good for agentic workflows as well. And so it's very pluggable. We have a lot of different scores, filters, and request control. And here's a performance chart comparing round robin scoring to KV cache load aware and like a KV utilization score. And you can see, we're reporting like in some cases up to 50x performance improvement to TTFT, mostly from taking advantage of prefix aware routing. Okay. Second well-lit path is pre-fill decode disaggregation. You heard a lot about this from the Mistral talk, so I'm not going to go into it too deep. But in llm-d, we're using Nixel, so the exact same code that the Mistral folks are using. We have a sidecar on the decode pod. The gateway will route first to the sidecar, which will then route to the prefill pod, which will do the prompt processing, send the request back to the sidecar, which then gets routed to the decode pod. And when that happens, it will pull the KV caches using Nixel from the prefill pod to the decode. And so, yeah, we use GPU direct RDMA via UCX, via the Nixel integration, which uses the KV connector API in vLLM. So this is asynchronous, zero copy, and zero memory overhead. So it pulls directly from the prefillers KV cache and inserts directly into the decoder's KV cache without any additional buffer as workspace. So one of the primary advantages of prefill decode disaggregation is it gives you specialization in how you parallelize prefill versus decode. And so, for example, you can do tensor parallel size 4 decodes with tensor parallel size 1 prefills. And then as the nature of your workload, the ratio of input tokens to output tokens changes, then we can vary the number of prefill and decode workers in the cluster. And as you can see here, so this is a chart that compares sort of like the x-axis is sort of like the aggregate throughput of the system. Sorry, that's the y-axis. And the x-axis is each individual user's output speed. So it's really like a throughput latency trade-off here. We see really good performance, especially in like middling request rates for the green line, which is disaggregated inference using 4 instances of vLLM for the prefiller at TP2 and only 2 instances of the decoder at TP size 4. So we like specializing prefill or specializing parallelization of the prefiller versus the decoder. And then that's compared to the orange line, which is 4 aggregated instances of vLLM running at tensor parallel size 4. And so one thing about this is you do have to tune the prefill and decode sizes to your workload. Okay, the third well-lit path that we have is KV cache management. So this is about like letting your KV cache state grow larger and larger to really take advantage of prefix caching. So here we have, this is also using the KV connector API. So we've got north-south KV management. So this is really about offloading to CPU memory and then to storage. So that basically effectively increases the size of your KV cache on a single node. And then we've got east-west KV management that it's a really distributed KV cache. So one pod can pull a KV cache from another pod. And so we have a couple of different integrations for this. One is llm cache. We also have support for Dynamo KVBM works in this as well. Right, and then the last well-lit path I'll talk about is something called wide expert parallelism. So this is really about large-scale multi-node serving for like sparse MOE models. So in this case, we have a single instance of vLLM spanning multiple nodes. And then it, basically to maximize throughput for large MOE models. Okay, so first of all, I'll talk about, so what is an MOE model? So Thomas mentioned these in his talk as well. They're really, so here's a diagram of an MOE model. So it's, all transformers are organized as attention, feed forward, attention, feed forward. And then, so coming out of attention, the output gets fed into a router. The router selects the top K weights and the top K IDs for every token. Each token then gets routed to the expert that corresponds to its top K IDs. And then each expert is a matrix multiplication. And then they get combined together according to their top K weights. So this is a form of activation sparsity. So each activation only takes into account the K experts that it gets routed to. So each token only, will hit, 8 out of 8 divided by 256 experts. And what we've seen over the past year or so is that essentially every large model that has been introduced in open source has been a MOE model. And this includes GPT-OSS from OpenAI, DeepSeek v3 and R1, Llama 4 from Meta, Qwen 3 from Qwen, and Kimi K2, including the thinking model that just came out today. And these have hundreds of experts, and each token only activates a handful per forward pass. This is an ablation study by DeepSeek, basically showing that as they activated fewer experts and added more and smaller experts, their models did better and better. And so really what we've seen is we've gone from this case of like, Mistral, which had like 8 experts to something like a DeepSeek V3, which has 256 in each token activating 8. This has introduced a bunch of challenges for how to serve these models. So one, for dense MOEs, you can just use tensor parallelism. This works pretty well. You can use a simple fused MOE model. An expert imbalance isn't too problematic. But for sparse MOEs, TP sharding becomes pretty problematic. Scaling out to multi-node becomes essential because they're huge. However, we can use sparse communication ops because of the activation sparsity of the router. And then because of the high sparsity, we really want to have high concurrency to get a high arithmetic intensity in our expert operations. So that's kind of good and kind of bad. Good because it can handle high concurrency, but bad because you really want to go to high concurrency. And then you do have to handle load imbalance across experts because there are so many, and because you may be at a very high concurrency multi-node setup. Okay, so then in response to all this, we've introduced a bunch of optimizations into vLLM to handle this. So we've gone from tensor parallel MOE layers to data parallel attention, especially for DeepSeek, where tensor parallel will replicate the KV cache, and expert parallel MOEs. We're using these sparse all-to-all dispatch and combine operations from DPP, from DeepSeek, and there's some kernels from Perplexity as well that we've integrated into vLLM. So coming out of the MOE router, you take the top KIDs for every token, and you pass there's a dispatch all-to-all operation, which looks at the top KIDs and will send the token to the correct node that has the experts that token needs to attend to. And this is fundamentally what lets us scale to multi-node. We've introduced expert parallel load balancing to basically we replicate experts to take the heavy hitters and kind of spread them across the cluster. And then we've also introduced dual batch overlap. These sparse all-to-alls are very expensive, and we can execute them at the same time that we do computation ops. Okay, so yeah, this is EPLB. Like I said, we replicate heavily used experts, and then we periodically rebalance the system according to the token distribution, so that we can, depending on the distribution of the input tokens and the tokens generated, different experts may be attended to more than others, and so we can dynamically rebalance the experts to handle this. And you can see, so this is a graph here. X-axis is time, Y-axis is balancedness. So balancedness is the maximum the mean experts, mean tokens per expert divided by the maximum number of tokens for any expert. And as you can see, it increases quite a bit after these rebalancing steps marked with the red dashed lines. And then another key optimization we added is dual batch overlap. So we take the batch that we're currently processing, we split it into 2, and then while one batch is executing the sparse all-to-alls, another batch is executing the computation ops like the experts and attention. Okay, and so yeah, putting it all together. So here's some performance numbers we ran on a cluster. So focusing on the decode first. So expert parallel size, this is the number of GPUs we're using. So we go from 32 up to 96. So that's 12 nodes of 8 H200s used for the decode. We have like a fixed workload here of 256 concurrent requests per expert parallel rank. And the thing that we see here is that as we increase the size of the deployment, we lose a little bit of performance, like it scales almost linearly. Like performance per GPU is almost constant. But the thing that we get out of it is a super linear increase in the KV cache size. So as we add more GPUs to the system, the higher concurrency per GPU we can handle. And then on the left, we have the prefill throughput. So in this case, we're really seeing expert parallel size is best at EP16 for the prefiller. And so what we do here is we have, one very large instance for the decoder, and we have a few smaller instances for the prefiller. The kind of phenomenon where we really want to like maximize the KV cache space for the decoder just isn't true for the prefiller because we don't have that many requests concurrently in flight. And they actually just have shorter sequence lengths because we haven't generated with them yet. And so, we're getting about, 2.2 to 2K output tokens per second per GPU. And so all of the, the kernel optimizations that we've added and the addition of fast EPLB and dual batch overlap and decode are really delivering compound gains. All right, Sasha.
All right. Ooh, loud. Thank you so much, everyone. We have another first at this vLLM meetup. This is the first time that we ever finished on time. And I promise you that. So 2 minutes early. Thank you to our speakers. You guys crushed it. A lot of work obviously goes into this. Two very quick things. I promised you this will get very technical. If you enjoy this type of content, Michael, our first speaker, and myself host bi-weekly vLLM office hours. We call them office hours because the initial idea was to come, have you guys come ask questions, but we've turned them into much more than that. Yes, you can still come and ask questions, but every other week, every other Thursday, we have amazing speakers from Mistral, Hugging Face, NVIDIA, Meta. The list goes on, and we dig into some awesome topics. So check them out. You can scan the QR code. Come join us. I know it's at 8 o'clock at night for you guys. That's the unfortunate part. As a fellow European, I know we dinner late, so if you want to join us over dinner, that's awesome. But honestly, seriously, if there's somebody in this community that wants to help us bring these office hours to a more appropriate time zone or a more appropriate time in Europe, talk to me, please. And then one last thing, I promised you a survey. Please, if you can scan this QR code, it's super quick. You can just give us 5 stars if you want and click submit. That would be appreciated. No, I'm just kidding. But thank you guys so much for coming. I think that we're going to skip the Q&A here, but all of us are going to be outside. So if you have any questions, if you want to continue this discussion, find us outside. And now let's have some awesome food, awesome drinks. Thank you, IBM, for the venue and for everything.